So yes, in the case of the right angle Sierpinski carpet, we will never toss our coin for this square in the upper right corner, but we will always automatically discard it. So for each level, we only toss our coin for the corresponding approximating squares in our sponge. And similarly, we can do this with the Sierpinski carpet. We can construct a random Sierpinski carpet where we always discard the central square at each level. And also we can construct the random Menger sponge. The Menger sponge is a sponge where in each of the faces we delete the central cube and we delete the overall central cube, and we can randomize this construction as well. And even though this inhomogeneous Mandelbrot percolation is very different from the homogeneous one, as I will show you, it's structurally more complicated, but they share some properties, namely the Hausdorff dimension in the inhomogeneous case are calculated in a similar way. So the Hausdorff dimension of this inhomogeneous Mandelbrot percolation is the logarithm of the expected number of retained level 1 cubes over the logarithm of the reciprocal of the contraction ratio, and this is the value almost surely conditioned on non-extinction. For example, in the case of the random Menger sponge, the almost sure Hausdorff dimension is logarithm 20p over the logarithm of 3. And in the case of the random Sierpinski carpet, this is the logarithm of 8p over the logarithm of 3. And the projections of these inhomogeneous Mandelbrot percolation to the coordinate axis were considered by a lot of people, by Decking and Grimet, Decking and Meester, Falconer and Grimet, and Barral and Feng. And we know a lot about the projection to the coordinate axis of this inhomogeneous Mandelbrot percolation, but the rational projections were not considered in here, but Shimon and Vago consider the rational projections of the random Sierpinski carpet, but we wanted to know a little bit more about these rational projections, what phases are possible, and particularly we considered the random Menger sponge, which is denoted by MP if the parameter is P, and we considered the projection to the space diagonal of the unit cube as it is illustrated in this figure, but we also considered some other projection. And in this case, but our main focus was on the projection to the space diagonal. And in this case, we're curious that what happens with the projection if we change the value of P. So clearly, if P is smaller than 0.15, which is 3 over 20, then the Hausdorff dimension of the random Menger sponge will be smaller than 1, almost surely. So nothing interesting happens, but then we have an interval of probabilities where the Hausdorff dimension of the original set is greater than 1, almost surely, conditioned on non-extinction, but the Hausdorff dimension of the projected set will be smaller than 1, almost surely. And we don't know precisely what is B1, where this interval, what is the right endpoint of this interval. Yes, and the next interval is the gray interval. We actually don't know if this interval exists or not. In this case, the Hausdorff dimension of the projected set is 1, almost surely conditioned on non-extinction, but the Lebesgue measure of the projection will be 0, almost surely. So as I mentioned, we don't know whether this interval exists, but we know that if we project to the coordinate axis, then this as an interval does not exist. It will be a single point. But it's possible, we don't know yet what happens in if we project to other directions. But what we know is that the purple interval exists. The left-hand point is B2, which we know precisely what is, but we know that it's between 0.15 and 0.1514. And it ends with 1/6. And this is where the Lebesgue measure of the projection is already positive, almost surely conditional non-extinction, but the projection does not contain an interval almost surely. This is interesting because in the deterministic case on the line, we don't know whether a self-similar set with this property exists or not. And then the next interval is between 1/6 and 1/4. And here the interior of the projection to the space diagonal will be non-empty, almost surely conditioned on non-extinction. And if P is greater than 1/4, then the interior of every projection will be non-empty, almost surely conditioned on non-extinction. And note that this bound is sharp, because if we project the Menger sponge, the random Menger sponge to the coordinate axis, then it will die out if P is smaller or equal to, I mean, the interior will be empty if P is smaller or equal to 1/4. So this is why it's very different from the homogeneous Mandelbrot percolation, because in that case, what we seen was this orange interval and this red interval, and we saw nothing in between. So either the Hausdorff dimension was smaller than 1, or the projection to every direction contained an interval, but we have a so much more colorful picture here. And in what follows, I will concentrate on the existence of interior point and the positivity of the Lebesgue measure. In the case when we project to the coordinate axis, the process is described by a Galton-Watson branching process. But in the case when we project to rational directions, it is so the underlying process is a branching process which is of multi-type, a multi-type branching process. And in the case of a Galton-Watson branching process, the most important thing to consider is the expectation of the offspring distribution. And the same rule in our case, in case of the multi-type branching process, will be played by certain expectation matrices. And these expectation matrices will be important because all of our theorems will be stated in terms of these expectation matrices. And so in what follows, I show you how to construct these matrices. I will show you in the special case when we consider the 45-degree projection of the Sierpinski carpet. The expectation matrices are actually just the matrices which corresponds to a deterministic system, and these matrices are multiplied by P. So now we will only consider, not only, but now we will consider the deterministic case, since we can get the expectation matrices by multiplying the resulting matrices by P. So the 45-degree projection of the Sierpinski carpet, the zeroth level approximation of the Sierpinski carpet is the unit square. And if we consider the 45-degree lines through the vertices of the unit square, then we see that it naturally subdivides the unit square into two shapes, this upper triangle and this lower triangle, which I will call pink, and the green triangle. And what is very nice is that if we go to level 1 from level 0, then in the big pink triangle and in the big green triangle, in these 3 columns of the big pink and the big green triangle. These shapes, the rescaled version of these shapes will repeat. So we call these columns as C0, C1, and C2, and C hat 0, C hat 1, and C hat 2. But we will actually only consider 3 columns, and this is because if we go to further levels, then we will see that a triangle which is of this pink type and the triangle which is of this green type are in the same column. So if we consider the subcolumns of these triangles, then we see that actually their columns are coincide. So the C0 column of the pink one will be the same as the C hat 0 column of the green one, and similarly with the first and the second column. So this is the picture what we should keep in mind when we construct the matrices. So how to do this? For each of the columns, we will have a matrix, and these matrices will be 2 times 2 matrices because we have 2 shapes, the pink triangle and the green triangle. The first row will tell us what happens in the big pink triangle, and the second row will tell us what happens in the big green triangle. Namely, the first column of the first row will tell us how many small pink triangle do we have in the big pink triangle. This is 1, so the first element will be 1, and the second will be 0, since we do not have any small green triangle in the big pink triangle. And the second row is filled similarly. In the big green triangle, we have 2 small pink triangles. So the first element is 2, and 2 small green triangles, so the second is also 2. And we do the same thing in the second column, which is the first column. Sorry. So we first fill the first row. It contains, the big pink triangle contains 2 small pink triangles, so the first element is 2, and 1 small green triangles, so the second element is 1. And the big green triangle contains 1 pink and 2 green triangles. And similarly with the last column, the big pink contains 2 small pink and 2 small green, and the big green does not contain any small pink and contains 1 small green triangle. And why this matrix representation is very nice, because eventually what we want to know is what happens if we go deeper and deeper to smaller and smaller columns. And if you want to know how many small triangles do we have in each of these smaller columns, then we can consider the corresponding matrix product. For example, if we consider the first column and the first column, subcolumn of this first column, and we want to know what happens, then we consider the product of A1 and A1, since we are in the first subcolumn of the first column. And we see that the big pink and the first row will tell us what happens in this column of the big pink, and the second row will tell us what happens in this column of the big green triangle. Namely, the big pink triangle will have 5 small pink triangles and 4 small green triangles, and the big green triangle will have 4 small pink and 5 small green triangle. And this can be done with any further level columns. Also, we don't have to only consider these. So this projection was quite easy, but we can consider more complicated projections. But for simplicity, now I will consider the right angle Sierpinski gasket instead. And one of its projections, and in this case, we have 3 shapes. And if we go to the the first level, because the contraction ratio is 1/2, in each of the big shapes we'll have 2 columns, and in these 2 columns the same smaller version of the same shapes repeats. And since we have 2 columns, because the contraction ratio is 1/2, we'll have 2 matrices, and we have 3 shapes, so we will have 3 times 3 matrices. You can check whether these are the actual matrices. Also, we don't even have to consider shapes. It's possible to only consider the projected IFS, the cylinders of the projected IFS. Here you can see that that you can just say that the cylinders has relative parts of and these play the roles of the shapes when it was a projection. So instead of shapes, we will have parts of relative parts of cylinders. And I will not talk more about how to construct these matrices, but this can be done for IFSs of the form where the common contraction ratio is 1/L, where L is an integer which is greater or equal to 2, and the translations are rational numbers. And if we constructed our matrices for our IFS, then there are 2 important notion, which is the Lyapunov exponent and the lower spectral radius. So for this set of matrices which contains A0 and 2AL-1, we consider the set of infinite words from these ABC 0 to L-1, and consider the uniform measure on it, mu. And by this norm, we denote a submultiplicative matrix norm. And for the Lyapunov exponent, we consider 1/n times the logarithm of the norm of an n-long product. And if we take the limit, then this will be the same for mu, almost every element of sigma. And this common value will be called the Lyapunov exponent. And similarly, we can define the lower spectral radius, which will be the limit as n goes to infinity, the minimum of the norm of an n product from our set of matrices to the power 1/n. And if we consider the positivity of the Lebesgue measure, then the Lyapunov exponent will be the important thing to consider. I wrote it here if you forget it. So again, what we have is an IFS, which is of the form where all the contraction ratios are 1/L, where L is an integer which is greater or equal to 2, and the translations are rational numbers. And assume that we construct our matrices, and all of these matrices is an allowable matrix. So each row and each column contains a positive element. Moreover, we have a product of these matrices which has only positive elements. Then we can consider this a random attractor, which we construct in a similar way as we did the homogeneous Mandelbrot percolation, although we toss, in this case, we toss the coin for the cylinders and not for the cubes of this IFS. And if we do this, then if we choose our probability to be greater than e to the power minus the Lyapunov exponent, then the Lebesgue measure of the set will be positive for almost every realization conditioned on non-extinction. But if we choose p to be smaller than this value, then the Lebesgue measure will be 0 almost surely. And so the Lyapunov exponent, as I know, is quite hard to calculate. So we have some checkable conditions. So let's denote the jth column sum of the ith matrix with CSIJ. Then if our probability is greater than the maximum of the reciprocal of the geometric mean of these column sums, then the Lebesgue measure of the set will be positive, almost surely conditioned on non-extinction. And similarly, we can give conditions for the existence of interior points, and our setup is the same. We have the same type of IFS, and we again have our matrices, and assume that we can find a product that has a row with only positive elements. And then again, we denote by CSIJ the jth column sum of the ith matrix, and the random attractor is denoted by lambda SP again. Then if we choose P to be greater than the reciprocal of the minimum of the column sums, then our random attractor will contain an interval almost surely conditioned on non-extinction. But if the probability is smaller than the reciprocal of the lower spectral radius, which is written here, then the random attractor will not contain an interval almost surely. And so the previous one was the sharp condition. This is clearly not, although we are trying to work on this. And we didn't give a checkable condition since this condition is already checkable, but in the case of the Menger sponge, instead of the lower spectral radius, we just use the minimum of the spectral radiuses. And this is all I wanted to say. Thank you for your attention, and thank you very much for the invitation.
Thank you very much, Vilma. So does anybody have anything to add or anything to ask? So I can see that Kara unmuted, but maybe you didn't want to talk, did you? So I had a couple of questions actually, but I don't want to sort of control the airspace. So first of all, going back to the statement of the that you had, where we had the kind of a line of values for the probability P, and then the various ranges where various things happen.
Oh, I'm sorry. Yes.
This one, yeah. So I was going to ask if you have any sort of estimates for the B1, but I think you said that B2, only thing you know about B2 is that it's between 0.15 and whatever was the next value. So there's nothing, you just don't know.
Yeah, I don't know anything about B1, nothing. Just that it's an interval. I know that blue is an interval, but nothing about B1.
And then, so this is all about the, so up to the sort of brown area at the end, this is all about the projection to the space diagonal. Is that right?
Yes.
But then the last statement is about all angles or all rational angles?
Yes, yes, about everything.
Every angle. So what about the statements for other angles in the values less than 1/4?
Oh, so for this, we should construct those matrices that I was talking about.
Oh, I see. Okay.
Yes, but if you want to consider one of these directions, then we construct these matrices and maybe can check the conditions. So
you had the Lebesgue measure and the interior point statements. But so if I understood the construction correctly, what you need for it to work is that somehow this process of coloring and labeling the types of subset that you get has to be something that terminates, which means that you have to have a rational angle, right?
Oh, yes, exactly, yes.
So is it somehow obvious that something happens for irrational angles?
Oh, it's not obvious for me, but we are also trying to work on this. Yes, we are curious what happens in irrational theories.
Okay.
Let me make a comment. It's Pablo Smerkin who knows a lot about this irrational situation. I don't think, but he has a number of theorems which gives conclusion in that direction. But this rational is very, very much different from the irrational.
Yeah, I can see that. But so from what you were presenting, you showed us these couple of examples, but this process of creating these deterministic matrices that describe the size of the projection, this is just generally true for any rational. You've shown that there's a method for making it work for any rational angle.
Oh yes, I think we can make the matrices, like create them, but it's possible that we cannot check these conditions because the matrices does not satisfy our further assumptions. It is possible.
Okay,
maybe.
I see.
So, but we can construct these, yes. But maybe it will be huge and yes.
Okay, I see. Yeah, it could be a very long process, right? And you could have very big matrices to deal with. Okay, so I think those were all the questions that I had at this point. Does anybody else want to ask anything?
Thomas has a question, Hannah.
Oh, Thomas has a question. Go ahead, Thomas. Don't be shy.
So just so when you consider the random models, you're considering this perturbation model. There are some other models of random fractals where the randomness is weaker. So sort of they're often described as homogeneous random fractals, where the randomness is the same across each level. Have you looked at those different models of randomness at all, or have you always just stuck to the perturbation models?
So if I understand the question correctly, we only consider these type of things that I was talking about.
Yes.
Thanks.
Thank you.
Okay. No hands raising. So let's thank Vilma again. Thank you very much.
Thank you.
And I'm going to pause the recording.